The DIBAL reduction of an ester to an aldehyde is a very niche reaction with a very specific set of reaction conditions. That's good news and bad news. It's good news because when you see them, you know exactly what they're going to be doing. It's bad news because then you have to remember what it's supposed to do. Hey there, OChemNinjas. When we describe the DIBAL reduction, we often describe it as a hydride reduction. And if you're learning about this reaction in class, you've likely previously learned about other hydride reductants, like lithium-aluminum hydride and sodium borohydride. LAH and sodium borohydride were good hydride reductants because they had a metal center with 4 bonds and a negative charge, so that one of these hydrogens could transfer to the carbonyl, reducing it down to another oxidation level. But that raises a bit of an issue. It's one of what I consider the biggest misnomers of this reaction. And I don't like misnomers, they confuse students. If we compare our typical hydride reductants to DIBAL reagent, the DIBAL reagent isn't actually a hydride reductant yet. It's got 3 bonds to aluminum. Aluminum is neutral. It is not nucleophilic at hydrogen at this point. So as drawn, diisobutyl aluminum hydride can't reduce any esters at this point. So I'll explain how we account for that when we go through the mechanism in a little bit. So we'll leave that issue off to the side for a little while. We could do a lithium-aluminum hydride reduction of an ester. It wouldn't form an aldehyde. The strong reductant would reduce the ester all the way to an alcohol. That's where the DIBAL reagent slips in quite nicely. The DIBAL reduction reaction is a partial reduction of an ester that reduces the ester only to the aldehyde. In our reaction notebooks, it is a reaction of an ester and the preparation of an aldehyde. In terms of the reagent for this reaction, it's an aluminum center bonded to a hydrogen and 2 isobutyl groups. The name of this reagent is diisobutyl aluminum hydride. When we write it on paper or an exam, we can write it in its condensed formula notation as 2 isobutyl groups aluminum hydrogen, or its initialism, DIBAL H, although some people omit the dash H and just write DIBAL. All of those are fine. The other quirk of these reaction conditions is it's run at negative 78 degrees Celsius, and it is kind of an arbitrary temperature until I tell you how we get there. Dry ice is solid carbon dioxide. When we add dry ice pellets to acetone or isopropanol, that liquid in that bath gets down to a temperature that's minus 78 degrees Celsius. Dry ice pellets and a jug of isopropanol are very cheap and almost certainly lying around a major research lab, so it's very easy to mix those together to make a cold bath that's minus 78 degrees Celsius. But interestingly, the temperature plays a critical role in this reaction. The reaction must be kept cold to successfully turn an ester into an aldehyde. Let's take a look at the DIBAL mechanism, see how it turns an ester into the aldehyde. As I mentioned before, aluminum only makes 3 bonds. It's neutral. It doesn't have a negative charge. It's not nucleophilic at hydrogen, so the hydrogen cannot directly attack the carbonyl carbon like other hydride reductions. Instead, we're going to bring in a property that we don't often talk about when we go through these metal-based mechanisms. Aluminum is very oxophilic. It forms very strong bonds with oxygen. Strong bonds like a rock, because they kind of are a rock. About half of the rocks in the world are aluminum oxides, and about the other half are silicon oxide. So the oxygen-aluminum bond is very strong and very stable. So the first step of this mechanism is a Lewis acid-Lewis base step where the oxygen bonds to aluminum. That forms the oxygen-aluminum bond in a reversible Lewis acid-Lewis base step. And now this is very interesting. Now oxygen does have 4 bonds. It does have a negative charge, and it does have a hydrogen that can be a nucleophile. This Lewis acid-Lewis base step is necessary to make the hydride source so we can do the reduction. Now, you might think then that this hydrogen can attack this carbonyl and push the electrons up onto oxygen, like we've seen with other hydride reductions. And that's fine, I'll allow it. We can draw those arrows. But that's actually not technically what happens here. Technically, given the geometry of this carbon, oxygen, aluminum, hydrogen fragment, the carbonyl's over here and the hydride's over here, and it can't geometrically actually get close enough to that carbonyl carbon to do the attack. This is technically not allowed geometrically. So technically, what happens in solution is that this hydride can't attack its own carbonyl. Instead, it attacks the carbonyl of a neighboring ester group, while its own carbonyl gets attacked by the hydride from a neighboring hydride source. We kind of get this cascade through the solution of one hydride attacking a different ester, while its hydride attacks a different ester, and its hydride attacks a different ester. But that's a pain to draw, so it's fine. We can draw it this way. The next intermediate after this step is actually really interesting. That step of the mechanism is not reversible. Hydride is not a leaving group. And we form this neutral oxygen-aluminum complex. Typically, at this point in the mechanism, we form the tetrahedral intermediate, and we would collapse electrons back down to kick out a leaving group. But we don't do that here. The important thing to note is this intermediate is stable at minus 78 degrees Celsius. That's why it's critical this reaction stay cold. And it's why we use such an unusual reagent. I mean, diisobutyl aluminum hydride is kind of an awkward structure. Through several iterations, we developed this precise structure precisely because this intermediate is stable at cold temperatures. That allows us to continue doing the hydride reduction of the carbonyl, and everything just kind of sits here until we've exhausted all of the DIBAL. If we went with our traditional route, If we dropped a pair of electrons down and kicked out the ethoxide group, we would make the aldehyde, but we'd still have a hydride source. If this weren't stable cold, when we formed that aldehyde, the DIBAL would reduce it again, and we would get the alcohol, the same thing we got with the lithium aluminum hydride. But by using this unusual reagent that's stable at cold temperatures, everything sits here until we exhaust the hydride source and no more reduction can take place. That's the reason for the unusual conditions, and that makes this reaction very cool. Now we're ready to quench the reaction. We use water for our quench for this reaction. And we use water because of what we talked about earlier. Aluminum is very oxophilic. The oxygen can form a bond with its aluminum, building up too much electron density around aluminum, breaking the aluminum-oxygen bond, reforming the carbonyl, and kicking out the ethoxide leaving group. What does the result of these arrows form? Pause the video, see if you can draw the next structure as a result of these arrows. The result of these arrows is our aldehyde product. This gets us our aldehyde product. This is how DIBAL partially reduces the ester to the aldehyde. And this mechanism is why this is one of my favorite reactions in organic chemistry. It's one of the unsung heroes in organic chemistry. Being able to dial in the correct oxidation level is an important skill for a synthetic chemist. Lithium aluminum hydride is a strong reductant that reduces this molecule 2 oxidation levels to an alcohol, and the DIBAL reagent is a complementary reaction that reduces the ester 1 oxidation level to the aldehyde. This is a very handy reaction to have in your synthetic toolkit. This is our reaction card for the DIBAL reduction of an ester. The three-phrase sentence for this reaction: an ester plus DIBAL makes an aldehyde. We need to know that three-phrase sentence in all possible combinations. An ester plus DIBAL makes an aldehyde. DIBAL turns an ester into an aldehyde, and an aldehyde is made when an ester is treated with DIBAL. The important note for this reaction is it must be kept cold. That tetrahedral intermediate is only stable at cold temperatures. If we had warm temperatures, that tetrahedral intermediate would collapse to the aldehyde, and more DIBAL would come in and would reduce it to the alcohol. Has to be kept cold. And some tags for this reaction: it's a non-regioselective reaction. We're not choosing between reaction sites. It's non-stereoselective. We're not even forming a stereocenter in our product. And this reaction is a net reduction. The ester is at the 3 CZ bond oxidation level, and the aldehyde is at the 2 CZ bond oxidation level.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.